All right, so this is our second set of video notes talking about solutions. And rather than spend some time in class going over what you just learned all week in the lab, we're going to talk about it here, and you can fill in your notes. You should have gotten a set in class. If not, I have uploaded those to Google Classroom as well. So let's talk about solution formation and rate, how fast solutions form. So as we talked about before, there's three factors that affect how fast a solution forms. The first one we're going to talk about is agitation, which is stirring. The whole idea is it comes back to collisions. The molecules between the solute and solvent have to actually touch and collide in order for the solvent to be able to pull it into solution. So if you increase collisions, you're going to increase the rate. And by stirring or agitating it, you are definitely causing those molecules, you are physically causing them to collide more often. Because of that, the dissolving rate increases. So if I were to ask you between these two pictures, which one would dissolve the fastest, temperature is the same. They both have ice cubes. Now we do see the cube on the bottom and the powder on the bottom. We're not going to look at that. We're looking at the agitation part of it. So A has no spoon, B has a spoon. B, if everything else was held constant for a control variable, would dissolve faster. So A is slower than B. Our second factor we investigated was temperature. The higher the temperature, remember, temperature is a measure of kinetic energy, so that means our molecules are moving faster. Well, if they're moving faster, so here are slow molecules, low temperature, collide not so fast, but as you raise the temperature, they start moving faster, and you're going to collide more often. If you collide more often, then you are naturally going to start increasing the number of collisions, and more frequent collisions, more forceful collisions, dissolving rate increases. And here we have hot tea and iced tea. Which one would dissolve faster if everything else was held constant between the cold and the warm? It would be the hot tea. So C, ignoring the spoon, would dissolve faster. And our third factor was surface area. Now surface area is inversely related to particle size. We saw that with our sugar cubes. Big cubes, but a lot of particles were held inside. So the idea is that smaller particles, you're breaking apart those cubes of sugar, you're exposing all of those molecules on the inside. If you're exposing more surface area, you're going to increase the number of collisions between the solute and the solvent. So smaller particles actually is greater surface area. Bigger particles, less surface area, less collisions. So the dissolving rate increases here. And here we have a picture of a sugar cube. So a lot of molecules are hiding inside of that structure, cannot collide with the solvent, going to be a slower rate, versus the powdered sugar, same mass, everything else, that would dissolve a lot faster. So A would be slower than B, ignoring the spoon. And this is just a graphic to show you what we're talking about when I say those molecules are hiding on the inside. On the left side here, we have our sugar cube, and the solvent is the red. That's our water. It can only collide on the outside of the cube, and the only way it's going to make it to the inside is if these solvent molecules pull off the outer layers, and that takes time. So the fewer solute-solvent collisions, it's going to dissolve slower. Versus our powdered form, or a granulated sugar, those solvent molecules are free to come inside of that structure and collide with those molecules that would have been hidden before. So you have more solute-solvent collisions, and it dissolves faster. All right, that's a summary of what we did last week in the lab. Very simple concepts, but you guys did a great job in the whole design process and the engineering of your experiment. So let's move into types of solutions. Now that we know what affects how fast they form, let's talk about types. But before we do that, let's talk about solubility, because that affects the type of solution that we're dealing with. So solubility is defined as the amount of solute that can dissolve in 100 grams of solvent. In our case, we generally talk about water. And when we do amount, we are mostly talking about grams because that's what we measure in the lab. Now there's 3 types of solutions where solubility ties in. You've probably heard of this before. It will be your unsaturated solution. Think of it's too little. We have our saturated solution, just right, and our supersaturated solution. We have too much solute dissolved in that solvent. And this picture, too hot, too cold, just right. Think about Goldilocks and the 3 bears. That is an analogy for our types of solution. Alrighty, so let's talk first about that unsaturated solution. You are able to dissolve more solute. Unsaturated does not have enough of the solute dissolved. So this picture kind of shows you over here on the left-hand side, we have only a couple of solute particles and lots of space to dissolve more. You could go ahead and dissolve some more and actually get up to the saturation point if you wanted to. Once you're at the saturation point, that's when you start to have that nucleation you see here, and you would start seeing solid. But we're talking about an unsaturated solution, so more solute. All right, saturated. So we've added. All of a sudden, we can't add any more. That's when that solvent is so packed full of molecules that it just doesn't have any more room to fit another molecule in between all of the molecules. And so we get to this point where we have an equilibrium. The dissolving rate, which you see here, are ions coming off, and the crystallization rate, the ions that are dissolved coming back onto the solid, are going to be equal. So dissolving rate equals crystallization rate. On the macroscopic level, from our human eye, we see nothing happening. Can't see anything. It still looks like, just a solution, homogeneous solution. On the microscopic level, it is moving. Those ions and molecules are moving in and out of solution constantly. Very dynamic. So that's what that says. The molecules and ions are constantly moving in and out of solution. And then we have our third one, which is a fun one. And we take advantage of this in, if you've ever played sports and you've gotten a sports injury, all of a sudden this coach busts out this gooey package and he pops it and it all of a sudden generates a bunch of heat. And it gets all solid. That typically is a supersaturated solution. And as he pops it, he's basically telling that supersaturated solution it's done, and it crystallizes out and it releases a whole bunch of energy when it does that, and that's the heat you feel. So a supersaturated solution contains more solute than it can hold. So for example, and you're going to see a video in just a second, this looks like just water. Homogeneous solution, colorless, transparent, liquid. But what those tweezers are holding is a tiny, tiny little crystal right there. And that's going to serve as a nucleation point for all of the molecules that are being forced into this liquid right now. So we drop that seed in, and right where it drops, all those extra molecules in that solution are clamoring to get out, and so they grab onto that seed crystal, and that's their point where they can kind of just start to turn into a solid. And then ultimately it will keep crashing out into solid until all of the extra solute has come out of solution. The liquid itself still is saturated, but we have the extra solid out. The way I like to think about this is, a great analogy is if you have, let's say, dead of winter, we have 200 kids in my classroom. 200 kids, and they're standing upright, shoulder to shoulder. It's not so bad because it's cold, it's winter. But let's say, all of a sudden gets really warm. The air conditioning's not working. And you have teenagers. We have hormones. We're doing all sorts of stuff. We're like standing there and so close to one another. We're starting to sweat. We're starting to smell. But you can't get out of the room. That would be your supersaturated solution. So you're standing there hot and sweaty. You're desperate to leave the room because it's so smelly and hot. And then all of a sudden, someone comes along, like EJ, and opens the door. I bet you the people closest to the door are going to be the first ones out. They're going to be running and taking deep, nice, cool breaths outside that classroom door. That's exactly what you have here. So over here is our room packed full of teenagers, hot and sweaty. And then the middle one, B, represents the door opening and allowing some point where we can escape that situation. And on the right-hand side, we have all of our students outside of the classroom. And there's some still inside because now that everyone's left, they're A-okay. All right, so this is a video to show you what a supersaturated solution would look like. This is sodium acetate, and it's called hot ice. This is what you would see in those hot packs because as it crystallizes, oh, really? Oh, boy. All right, that didn't go very well. But you can look it up. It's a fun video. That's too bad. Oh, maybe. Maybe. Watch this. Yeah. I got skills sometimes. All right, here we go. So this is a petri dish. It's filled with a saturated solution of sodium acetate, just super saturated, and they just provided one little spot. And now all those extra molecules, those teenagers in that classroom are running out that door, and they're turning into a solid. It looks alive almost, but all it is ionic compounds. Basically, all those ions are crashing into one another and saying, "Get me out of here." And it's very exothermic, which we'll learn about later. It releases a whole bunch of heat, and that's why they use it in hot pads. So here they have the crystal on the bottom, and they're pouring the supersaturated solution on top of it. This is really neat. Watch this. It happens so fast that as they are pouring that supersaturated solution onto the crystal, it is forming crystals immediately. So all the little teenagers, all the little molecules that are in this liquid, as soon as they touch this solid right here, they are coming out and getting happy. It's really kind of cool. It just builds up. You ever done those like sand castles at the beach where you do it with the wet water? Looks very similar to that. So anyway, that kind of gives you a kind of little cool, oh wait, this is, yeah, it's just more of the same. But you can go ahead and look this up. Supersaturated. It's sodium acetate on YouTube. Alrighty, let's go back to our PowerPoint and finish this up. Solubility curves. We're almost done, about halfway done. So solubility curves. We can look at how soluble something is through a solubility curve. And this tells us the relationship between our unsaturated, saturated, and supersaturated solution. So on your set of axes, you're going to draw this. On the x-axis, we have temperature. On the y-axis is our solubility, which is really just mass per 100 grams of water. And a solubility curve really is just a curve. That's it. And there are three parts to this graph. There is the line itself, and that represents the saturation point at any point in time. Then you have above the line, so because we're going up on the y-axis, that's more mass at any temperature. So once we pass the saturation point up here, represents a supersaturated solution. And then we also have our unsaturated, which would be below the line, meaning we haven't added enough. This one I like because it gives you a nice visual of what the molecules are doing. So here we have our unsaturated down on the bottom, not, less dense molecules. The line represents the saturation point, and up at the top, the supersaturated, you have all those molecules packed close together, just like our teenagers in that hot, hot room. All right, that's pretty much it for solubility curves. We're going to get back into solubility in a little.
Some time ago, we made a few videos regarding hot ice, and we feel it.
That was weird. YouTube. Okay, so anyway, molarity. We're going to talk about how do we quantify that solubility? How do we quantify how concentrated some of these solutions can get? Now, we saw this when we were dealing with that acid. It was a 6 molar acid, and that's what this is. I'm going to teach you how to do that. We're just going to get a little sneak peek into it. We're going to do some more on Monday and more on Thursday with molality, but it's a very common way for us to measure concentration. And if you ever think about drinking water, this is so key. What is in your drinking water? Is it just water? No, it's not. We actually add fluoride. There's other ions like calcium and magnesium and other things in there that just happen to be. And the government actually regulates the concentration that is allowed for all of these chemicals in our drinking water. Because if they didn't, I mean, you can look at the pictures. If they didn't regulate concentrations, we could, yes, you know what I'm going to say, we could die. And even there's debate about the whole fluoride thing now, because it actually causes something called fluorosis, which is, it has to do with your bone density causing osteoporosis and things like that. So let's learn very quickly how to do molarity. What is molarity? Well, molarity, there's two different types. When we're talking about solutions and molarity, we tend to talk about dilute and concentrated, which is really measures of a unsaturated solution. So a dilute solution has only a small amount of solute, whereas a concentrated solution has a large amount of solute. And this picture gives you a visual. And we've played with copper sulfate. We know what it looks like. Just a little bit of copper sulfate is a dilute solution. You add more, it gets a little darker. You can visually see it's getting concentrated. And if you add more over here down the far right, that's your concentrated solution. So how do we actually quantify those concentrations? Through molarity. It's defined as the number of moles per liter of a solution, but we have a handy dandy equation. Very simple. Moles of the stuff that you are dissolving, your solute, divided by the volume in liters. Very easy. And we use this capital M to represent molarity. Do not use a little m. That's meters. Okay? All right, here we go. And don't use MOL because that's mole, so use big M for molarity. We're going to do two quick examples, and that'll be your sneak peek into concentration. We'll continue later. So the example we have before us is a solution has a volume of 0.25 liters and contains 0.70 moles of KCl. What is its molarity? Well, just use the equation you see right there. Moles divided by liters, and this problem is actually super easy because they give us moles and they give us liters. No conversions, nothing. We just plug it in. So our molarity is going to be the 0.70 moles of KCl. And notice I am still keeping number, unit, and substance, divided by the 0.250 liters. Now, if I were live in class, I would ask you how many sig figs in our final answer, and you would say, hopefully 2. Alrighty, and when you do that division, you get 2.8 molar KCl. So again, number, unit, substance. Very easy calculation. Now, they're not always going to be that easy. For example, in this one, if you were to look at this, what is the big difference? Well, 1, we're given grams and not moles. So what do? 2, it's not in liters, it's in milliliters. So this one's easy. You just divide by 1,000, so it moves over 3 times and becomes 0.5. Well, since we don't have moles, that is going to be our first step. So you'll take your 10 grams of NaCl, multiply by the conversion factor. 1 mole of sodium chloride is 58.44 grams. Now, I didn't do the molar mass calculation because we've been doing it for months. You should know how to do that. If you don't, please come in for help. So 10 divided by 58.44 is going to give you 0.1711. Now, I carried an extra sig fig because this is a multi-step problem. I don't want to round too early. Now I have moles and I have volume. So I'm going to go ahead and plug it into our molarity equation, moles divided by volume. So I go ahead and I take my 0.1711 moles, which I calculated up here, divide by that 500 mils, remember, just move the decimal over 3 spots to get to liters. So divide by 0.500, and our final answer should have how many sig figs? I'm assuming you said 3 because you're awesome. You should get 0.342 molar NaCl. Number, unit, substance. And we are done. Awesome sauce. Thank you so much for joining me today.